Hello everyone. So today we will study compressor. Okay. So what is the compressor? The function of compressor is to compare the gases or vapor. Compress, sorry. The function of compressor is to compress the gases or vapor from lower to higher pressure, and for that work input is required from some prime mover. Okay. We use the prime mover so that we can provide the work input by which we can increase the pressure. Okay. So there are some classification of compressor. The first one is the based upon working principle. Based upon working principle, the first one is positive displacement compressor. So in this compressor, the pressure of gas is increased by decreasing its volume in a confined cylinder. So please keep in mind this term, confined cylinder, is very important here. Confined cylinder. In a confined cylinder, the pressure of gas is increased by decreasing its volume. Confined cylinder, it basically denotes that here a specific volume is just rated to compress the gas. So this is for one cycle, this becomes the same. So the work is applied on this confined space or this specific volume to increase the pressure. That's why the positive displacement term comes here. Okay. So the pressure of gas is increased by decreasing its volume in a confined cylinder. That is, rise in pressure is obtained by positively displacing fluid to a lower volume. Okay. Positively displacing fluid to lower volume in a confined cylinder. So the very first and basic example is the reciprocating compression. And the second one is the dynamic compression. What is dynamic compression? Dynamic compressor. In these compressor, high kinetic energy is given to fluid by a rotating element called rotor. And then this high kinetic energy is transformed into pressure in the diffuser. That is, rise in pressure is obtained due to dynamic action of gas. Okay. So once again, in these compressors, high kinetic energy is given to fluid by rotating element called rotor. There is a rotor involved here which rotates, and by the rotation of this rotor, the high kinetic energy is transformed into pressure. Means kinetic energy here transform into pressure energy with the help of rotor mechanism. Okay, in the diffuser, uh, there is a diffuser in which high kinetic energy is converted into pressure because as fluid flow through the diffuser, its pressure increases. So energy increases. That is, rise in pressure is often due to the dynamic action of gas. So the example is centrifugal or axial flow compressor are the dynamic compressors because rotating elements are involved. Now, based upon the pressure developed, there are three types of compression. Low pressure compression, which is increases the pressure up to 10 bar, medium compression up to 80 bar, and high pressure compression above 80 bar. So the limit is 10 and 80. Lower than 10, low pressure, 10 to 80, medium pressure, and above 80, high pressure compression. Based upon pressure ratio. Based on pressure ratio, three type of compression: fan, blower, and compressor. So the limit is 1, 1.1, and 2.3. So 1 to 1.1 is called fan. I mean, uh, fans are operate between 1 to 1.5 pressure. This is the pressure ratio, PR upon P, pressure ratio. Okay, and 1.1 to 2.3 blowers act, and the compressor above 2.3 compressors act. According to the volume handling capacity, handling capacity, there are three types of compressor: small capacity, medium capacity, and large capacity. Small capacity compressor are 9 meter cube per meter. Its capacity is 9, so the limit is 9 and 3000 meter cube per minute. Below 9, small capacity, 9 to 3000 medium capacity compressor, and above 3000 large capacity compressor. Now, reciprocating compression. What is reciprocating compression? So, the working principle of reciprocating compression is very simple because here piston cylinder is involved. It works like the piston cylinder engine. Okay, so here what happens that when the piston compresses the fluid, the first there is a suction takes place. Suction takes place, then the starting valve, this suction valve opens and the fluid enters in the chamber, and then it compresses the fluid. It compresses the fluid, and the delivery valve or discharge valve is closed till the compression of the fluid. And when it reaches the required amount of the pressure, the discharge valve opens, or when it continuously move left or right or up and down motion it creates, so the pressure continuously increases because there is a discharge container involved here. So as the fluid goes from here to here, the pressure continuously increases. So this is the basic funda of the reciprocating compressor. This from this figure we can also see that when suction takes place from here 1 to 2, that it compresses. The compression involves a polytropic process. It depends that it is isothermal, isentropic, or any polytropic process, and discharge takes place. Okay, so its drawbacks are intermittent. It it works intermittent operation. It is not continuous. Can be used in gas turbines. Can't be used in gas turbine. In gas turbines we can't use it. And its volume handling capacity in 8 to 12 meter cube per minute, which is very less, and efficiency is very less, and maintenance cost is very high because of there is a highly moving components are involved here, and the RPM is very less. Okay, so it is basically used in air drilling, okay, air filler station, like that, not very widely used. So in construction, it consists of piston cylinder arrangement with two valves, one on the suction side and other on the discharge side. These are simple automatic valve which works due to pressure difference across the valve. These compressors are used in air conditioner, refrigerator, and air filling station, air drill, air brake, spray painting industries, mining work, etc. So the main advantage of using these compressors are that is the reciprocating compressors are that it is capable of developing very high pressure. Okay, it is low in investment and low space requirements are involved. Capable of developing very high pressure up to 1000 bar it can develop, and the investment cost is very low and the space requirement is also very low. The disadvantages are intermittent supply, low volume handling capacity, that is 8 to 12 meter cube per minute, poor efficiency, high maintenance cost, and low RPM. These are some basic disadvantages of the reciprocating compression. Now, work input required without clearance volume. So, without clearance volume, if we want to calculate the work input, see from here that work input per cycle is given by area 1, 2, 3, 4, 1. Okay, like 1, 2, 3, 4, 1. This is the area. I mean, this work is we have to provide. Okay, so work done by the air during suction is equal to suction pressure is equal to P1, P1, V1 minus 0. The suction work is this P1, V1, and the work done on air during compression. During compression, the work will be this P1, V1 minus P2, V2 upon L minus 1. That is compression work. Now the work done on air during discharge, which will be P2 and 0 minus V2. It is minus P2 V2. So the total work done per cycle will be P1 V1 plus P1 V1 minus P2 V2 upon N minus 1 minus P2 V2. So P1 V1 minus P2 V2 will be 1 upon N minus 1 plus 1. Okay, P1 V1 minus P2 V2 we have taken common. So this will become N upon N minus 1 P1 V1 minus P2 V2. So the work done per cycle from a compressor, we are getting that, let's write it here, that P1 V1 minus P2 V2 into n upon n minus 1, that is work done per cycle. Okay, this is the work done per cycle of the compression. As compressor work is always negative, so taking only the magnitude, we will take only the magnitude. Okay, so it gives the magnitude. That's why we have written here like P2 V2 minus P1 V1. Okay, because P2 V2 is uh, more here. So let us take P1 V1 common. We want to find out some uh, interesting things. So we'll get this. So from process 1 to 1 P1 V1, that is the polytropic process. You can see the figure. And from that process V2 upon V1 is equal to this. And when we'll put to we'll replace this V2 upon V1, we'll get this, and we'll get actually we want to find out the work in terms of the pressure ratio. So we'll get the work done is equal to n upon n minus 1 P1 V1 P2 upon P1 raised to the power n minus 1 upon n minus 1 kilojoule per cycle is the work done. Okay, so P1 here P1 will be written in terms of kilopascal and V1 is meter cube per cycle. If n is the RPM, then power will be work done per cycle into n upon 60. This is the power required to a compressor. Okay, so the next topic is the isothermal efficiency. What is isothermal efficiency? So from this figure, we are seeing that uh, at from point 1, when we are going from point 1 to let's say 2, here the polytropic index is 1.3, then 1.4, then 1. So here we are saying that the work requirement is getting decreased. It means that we can see here that this amount of work, if we are uh, the compression process, if we are following the isothermal process, then the work requirement is lesser than any other polytropic index. Okay, so practically it is not possible to compress the gases isothermally, because that would be very slow process. Okay, and that much of slow process we can't sustain. Okay, that's why practically we usually use the polytropic index from 1.25 to 1.35. Okay, so here isothermal efficiency can be defined as the isothermal work. This is the type of the ideal work, because for that work the compressor work is lesser, because efficiency is the what is required divided by what is the maximum. Okay, what is the maximum possible. So the required is the isothermal work. We want the isothermal work and the actual work. From here we are defining the isothermal efficiency of the compressor. Okay, and the isothermal will be work will be calculated with the help of the compression work by isothermally. So the isothermal work can be written as P1 V1 ln P2 upon P1, and actual work is this. So the isothermal work we can calculate, which we will get that 80 to 85% isothermal work we are getting if we are using the polytropic index 1.25 to 1.35. Okay, then we are getting 80 to 85%. It means that 1.25 will be 1.25 will be this, and 1.35 will be this, because the for maximum efficiency the work polytropic the isothermal work will be I mean compression work will be isothermal. For that, as a polytropic index will be 1, so that index will be closer to 1 for maximum efficiency. Now let's see that what is the effect of the clearance volume in the compressor. Work input required with clearance volume. Okay, so from this figure, we have taken a clearance volume that is given from here. I mean, this is the clearance volume. Okay, so first suction takes place from this to this. The thing is that here from this figure we can see that suction actually starts from this place. Okay, this place. So suction, when suction starts from here to here, then it compresses polytropically, then it discharges at constant pressure, Then again expansion takes place, and when the expansion takes place, the actual volume is getting this much. We are getting actual volume this much amount. That's why this is considered as the suction volume. Okay, and the suction volume we know that Vs is equal to pi by 4 d square. And the diameter of the piston is called bore, and the length of the piston I mean cylinder is called stroke. Okay, so in actual working, there is always left a minimum volume between the piston and cylinder head, termed as clearance volume. It is provided for thermal expansion, okay, and valve tolerance, and to avoid piston striking the cylinder head. That's why clearance volume is important to build. Okay, so clearance ratio can be given as VC upon VS. Clearance volume upon stroke volume. That is usually taken as 5%. Now, what is the work input per cycle? So, work input per cycle is given by the area 1, 2, 3, 4. As we have seen in this figure, work input per cycle is this 1, 2, 3, 4. Okay, so work input per cycle will be W12 minus W43. W12, I mean the work input per cycle is this W12 minus W34, because this work is we are applying, this work we are getting. So W12 minus W34 will be, that is without clearance volume, without clearance. Okay, let me check once again in case of this. Actually, I think that is uh, some problem is this. I think that is with clearance volume. This should be with the clearance volume. Sorry, that is with clearance volume. Okay, so W12, as we have calculated earlier, uh, the compression work 12 is given as this pressure ratio, and the 43 this pressure ratio. But P2 is equal to P3 and P4 is equal to P1. From this figure, we can say that P2 is equal to P3 and P4 is equal to P1. Then we can manipulate some of the things. So P2 upon P1 and P3 upon P4 can be written as P2 upon P1. Okay, so this all the terms can be taken collectively, and we can say that with clearance volume, the work done per cycle will be N upon N minus 1 P1, V1 minus V4, V2 upon P1 to the power N minus 1 upon N minus 1. So the extra term we are getting that this this term we are getting, otherwise every term is same. Here we can see the same. So the volume we are getting, volume will be replaced by V1 minus V4. That's it with clearance volume. So due to clearance volume, there is no change in work input required by compression. Due to clearance volume, there is no change in work input required by compression. Okay, the only difference, the actual volume of air delivered per cycle decreases. Actual volume of the air per cycle decreases. Thus, for the same volume to be delivered, number of cycles required increases. Thus, for the same volume to be delivered, number of cycles required to be increases. Number of cycle can be increases because we are getting the less amount of air, whatever we are getting without the clearance volume. So if we will calculate that P1 actual volume we are getting, that then P1 V1 is equal to mass of air RT1 actual mass. From here we can get the actual volume, that is actual volume V1 minus V4 we can get from this equation. Okay, now let's see the volumetric efficiency. What is the volumetric efficiency? It is basically called as breathing capacity. Like the breathing capacity of human is 60 to 70%. So uh, it is a term used to indicate the volume of air that is delivered during the total displacement of piston. It is the ratio of actual volume of air entering inside the cylinder to the piston displacement volume. So the volumetric efficiency can be written as actual volume upon swept volume, V upon Vs. Actual volume will be the swept volume minus V4 minus V3. Like we have seen in the figure that 1, 2, 3, 4. So the stroke volume will be Vs, that Vs minus V4 minus V3. Okay, sorry, the stroke volume is this. The stroke whole distance is stroke volume. Okay, so the stroke volume will be, sorry, let me delete it. 4, this is 4. So I would say that this is the Vs, and this is actual volume. So actual volume will be Vs minus V4 minus V3. That's it. So volumetric efficiency will be the actual volume upon stroke volume. So it can be 1 minus V3 upon Vs, V4 upon V3 minus 1, and V3 is equal to Vc. And for expansion process 3, 4, this expansion process, we can use the polytropic formula, and V4 upon V3 can be written as P3 upon P4, that is P2 upon P1 minus 1. So volumetric efficiency will get that. Let us write it. Volumetric efficiency, we are getting that 1 minus C, that is clearance volume, into P2 upon P1 to the power 1 minus 1 upon n minus 1 and minus s. That is the volumetric efficiency. And the work with clearance volume is equal to, uh, let us write it. Work, we are getting that work done per cycle is equal to n upon n minus 1 P1 V1 minus V4 P2 upon P1 to the power n minus 1 upon n minus 1. So here we can see the difference. It is n minus 1 upon n, and here 1 upon n minus 1. So should not be confused that both are same. P2 upon P1 is same, but the index is different. That is the in case of the work, the index is n minus 1 upon n, and in case of the efficiency, that is 1 upon n minus 1. N upon n minus 1 upon n minus 1 upon n minus 1 upon n, and for volumetric efficiency 1 upon n minus 1. Okay, so don't confuse. So if we'll conclude the compressor part, so I would say that for the reciprocating compressor, when P2 is equal to P1, there is no compression, but volumetric efficiency becomes 100%. P2 is equal to P1. Okay, so what is P2 is equal to P1? You can see when P2 is equal to P1, it is saying that when P2 is equal to P1, there is no compression, but volumetric efficiency becomes 100%. Of course, because the stroke volume will be the actual volume, equal to the actual volume. And for a fixed value of P1, as P2 is increased, for a fixed value of P1, as P2 is increased, how much the pressure will be increased, the efficiency decreases and finally becomes 0 when the pressure ratio is 1. When the pressure ratio will be, when the pressure ratio is 0, of course. Like if like when pressure ratio is this much, sorry, when pressure ratio is this much, then the volumetric efficiency will be this. If we are saying that volumetric efficiency is 0, then from this formula P2 upon PL V1 upon C plus 1, condition for 0 efficiency, then it will come down to this, because the stroke volume is this and the actual volume is this. So yes, of course the volumetric efficiency is 100% here, but for that I mean, I mean, volumetric efficiency will be 100% for P2 is equal to P1, and zero volumetric efficiency will be zero for the pressure ratio of this much. So for the pressure ratio, P2 upon P1 is equal to 1 upon C plus 1 raised to the power n. This is for volumetric efficiency becomes zero. Okay, so here we can see that increase as we increase the pressure ratio, so we can see that the area increases, so work input will be increase. With increase in clearance ratio, volumetric efficiency decrease. With increase in clearance ratio, as we increase the clearance ratio, the volumetric efficiency decrease. From this formula, we can see that as we increase the clearance ratio, volumetric efficiency decrease. With increase in expansion coefficient, volumetric efficiency increase. It means n increases, volumetric efficiency increase. When we increase the expansion coefficient, and so when we increase the expansion coefficient, what is happening? Oh, when we increase the expansion coefficient, this decreases, so this decreases, so this decreases, so this increase. Increasing the expansion coefficient. Okay, from here we can also see as we increase the expansion coefficient, like from here to here, as we increase the expansion coefficient, volumetric efficiency increases. Sorry, expansion coefficient is increasing in this direction. Okay, volumetric efficiency increases, and with increase in clearance ratio, volumetric efficiency decreases. Yes, of course, the more you have taken the clearance volume, the less air you will get, the less actual air, I mean, the less will be the actual volume occupied by the air. So the volumetric efficiency will decrease. So the more will be the clearance ratio, the less will be the volumetric efficiency. That's so simple. Okay. So I'll sum up here. Okay. Thank you.